So I'm first of all very honored to have this opportunity to speak to you on a very important issue. And today I'm going to focus on greenhouse effects of methane, nitrous oxide, and carbon dioxide, all gases that are connected with farming activities across the world, every country of the world. This is work that I've been doing with a good and very talented Canadian colleague, William Van Weingarten. I think William has spoken to this group before. So some of what I will say, I'm sure will overlap what you've heard from William in the past, but William is at York University in Canada. Like me, he knows a lot about radiation transfer in gases, and we're still working together, focusing recently on clouds, which are considerably more complicated than clear air, as I think everyone can guess. So I thought I'd begin, since this is sponsored by the Irish organization, with the discoverer, really, of greenhouse gases, the Irishman, Anglo-Irishman, John Tindall. And he really broke open the subject and brought it from sort of a just so story into quantitative science. So here's his description of the greenhouse effect in 1859. When the heat is absorbed by the planet, it is so changed in quality that the rays emanating from the planet cannot get with the same freedom back into space. Thus, the atmosphere admits of the entrance of solar heat, but checks its exit. And the result is a tendency to accumulate heat at the surface of the planet. Now, that's exactly what you hear today from NASA and NOAA. So John Tindall got it right, more than 100 years ago. NASA and NOAA are still trying to get it right at the cost of many, many tens of billions of dollars. And if some of the advocates of extreme policies have their way, the whole world will be spending trillions of dollars for nothing. Well, let me say a little bit more about my hero, Tindall. This was the apparatus he used to measure absorption of thermal radiation by gases, and his thermal radiation source over here was a little can of boiling water. So this can was covered with soot so that it would emit heat radiation easily. He had a screen here, he could block it off. And then he had a long tube that he could put different gases into and let the heat radiation shine through the tube to a thermopile detector here that could measure the amount of thermal radiation that fell on it. Tindall was a smart guy, and he recognized that heat radiation will not go through glass and most other transparent materials. And with great effort, he had managed to get rock salt windows for his tube. I'm still amazed to see people like Bill Nye, the science guy, and Al Gore do experiments with infrared with glass, when Tindall himself knew 150 years ago that glass doesn't transmit infrared radiation. But sort of shows how far we've degenerated. Anyway, Tindall, with this apparatus, measured the absorption of carbonic oxide, that's what we would call carbon monoxide today, carbonic acid, that's CO2, carbon dioxide. Here's nitrous oxide, that Brussels is using to beat farmers on the head with. Hydrogen sulfide, the rotten egg smell. Marsh gas, methane, the other key gas that's being used to victimize farming communities around the world. So Tindall had them all in the 1860s. And if you look at his measurements, they're pretty good. They don't differ a lot from what we know today. And Tindall was very grateful for greenhouse gases. And of course, he early discovered by far the most important greenhouse gas was water vapor. He knew there was an effect from CO2, but it wasn't very big compared to water. And he says aqueous vapor is a blanket more necessary to the vegetable life of England, and Ireland too, by the way, than clothing is to man. Remove for a single summer night the aqueous vapor from the air which overspreads this country, and you would assuredly destroy every plant capable of being destroyed by a freezing temperature. The warmth of our fields and gardens would pour itself unrequited into space, and the sun would rise upon an island held fast in the iron grip of frost. Well, that's actually quantitatively true. You know, if you remove all of the greenhouse gases from Earth's atmosphere, we would be a snowball, you know, floating around in space. Nothing could grow. Okay, so let me see if I can advance this. For some reason, I'm having a little trouble. So let's see whether yes. So here are the major natural greenhouse gases. It's important to know roughly what they look like. Water vapor is a bent molecule. There's a oxygen here and two hydrogens here. It looks like sort of Mickey Mouse upside down here, his two ears and his face. Carbon dioxide is a linear molecule with a carbon in the middle and oxygens on both ends, so it's straight, not bent like water vapor. Nitrous oxide, very much like carbon dioxide. You've basically changed the carbon to a nitrogen and the oxygen to a nitrogen, but to those who know a bit about quantum physics, the electron structure in these two molecules is almost identical. And finally, there's methane, which is a tetrahedral molecule. The tetrahedron has four corners, and on each of those four corners, there's a hydrogen. That's a four on the hydrogen here, and there's a carbon in the middle. So these are the key gases that control the temperature of the Earth's surface. Now, this is a very famous slide that many people show. It's a little bit deceptive, but because what it is showing is the transmission of radiation of various frequencies. This is visible light over here, radiation below 1 micron in wavelength, and that's what the sun emits. So this red curve over here is the emission spectrum of the sun at the top of the atmosphere. Right, actually, and over here is the emission spectrum of the Earth at much longer wavelengths. That's, you know, almost 100 times longer wavelengths, more than 10 times longer. And what you see is that the sun is heavily absorbed at very short wavelengths in the ultraviolet, absorbed and scattered, I should say. But there is this window where sunlight gets through just fine. So I'm looking out my window, it's still daylight here, probably still daylight in Dublin. And I can see a beautiful blue sky where the sun is coming through just fine. The blue is light that's been scattered by this Rayleigh scattering you see down here. Another one from another hero from the British Isles was Rayleigh, along with Tindall. And over here is transmission of infrared. Infrared is not transmitted nearly as well, long wave infrared. And so there's heavy absorption, mostly by water vapor. So here you can see why water vapor is so important. It covers most of the thermal spectrum of the Earth. Carbon dioxide is next most important. You can see it's quite a bit less important than water vapor because it's confined to such a narrow band of wavelengths. There's ozone, methane, demonized methane and demonized nitrous oxide. You notice that methane and nitrous oxide absorb nearly the same wavelengths of light. And so their overlap actually hinders either one of them from being as effective as it might be if they were in a clearer part of the spectrum. So now I'm going to have to say a little bit about physics. Jim O'Brien said talk all about physics, but I realized that that wasn't going to work, but I'll say a little bit about physics. And so this is two charges, a positive charge and a negative charge. And positive charge squirts out field lines. So these are lines of electric field that come out of the positive charge and into the negative charge. You can think of a little bit like currents of a liquid that flow through space. empty space, but the space is full of electric field. And if the charges move, then you can shake off the electric field and create magnetic fields at the same time, and they flow out from these oscillating charges into space, or vice versa. They can come in and be absorbed and force the charge to oscillate. But the key idea here is to get efficient radiation, you have to have a molecule that has a plus end and a minus end. It has to have an electric dipole moment. Nitrogen doesn't have that, which is most of the atmosphere. Oxygen doesn't have that. That's the other big fraction of the atmosphere. But greenhouse gases do have positive ends and negative ends. So that's the thing that makes greenhouse gases unique, that they have positive and negative ends that can oscillate at thermal frequencies, whereas nitrogen and oxygen don't. So here's an example in methane, the celebrated methane. And remember, methane has 4 hydrogens. This is probably impossible to understand at a first glance, and the figure is not all that great, but the big atom in the center is carbon, and the 4 littler atoms are the hydrogen atoms. Hydrogen atoms are slightly negatively charged. They suck electrons from the carbon, so the carbon is slightly positively charged. So you can see that the carbon can move with respect to the hydrogens in these 2 typical modes. Molecules have modes that they oscillate in, just like a tuning fork will oscillate at a given frequency. Molecules have a tuning fork like modes. And for the case of methane, the most important one is at 1311 wave numbers, and we'll come back to that. Many of the modes actually do not have separated positive and negative charges in the right configuration. So even though they oscillate, they don't radiate. They don't have a electric dipole moment. And without that, they're very, very poor emitters of radiation. Okay, now I'm going, this slide is the basics physics of radiation transfer. So I'm going to tell it to you in words. Then I'll just, for information, I'll show you how that starts getting translated into equations and eventually into computer codes to do calculations with numbers. But this is the basics. And so radiation going through the atmosphere can be absorbed. And so radiation is made up of photons, little quantity of energy, and a molecule, say of methane or a droplet of water in a cloud, can absorb that energy, and the energy goes away and it turns into heat in the molecule or heat in the droplet of water. And that heat is released to the surrounding air. So the molecule that's been warmed by radiation warms the surrounding nitrogen and oxygen by collisional contact. So that's absorption. The reverse can happen. Heat can flow into this molecule and force the positive and negative ends to start vibrating against each other, and then the molecule radiates. It creates photons instead of absorb them. So emission is important. So absorption and emission play equal roles. Emission, in fact, quite a bit more important for the greenhouse effect than absorption. And finally, there is scattering, where a photon comes in. It doesn't manage to deposit any energy or very trivial amounts in the atom or the molecule or the droplet of water or crystallite of ice, and it scatters before any heat has been transferred. This is not very important for greenhouse gases. It's completely negligible, actually, scattering, but it's quite important for clouds, which William van Weingarten and I are looking at now, and also quite important for short wavelength sunlight, blue light and ultraviolet light. It's this process that makes the blue color of the sky. It's called Rayleigh scattering. Okay, so I said this is really for getting a feeling for what's involved. You take those processes, which I've shown on the previous slide, you translate them into equations. And so this sort of incomprehensible equation tells you how radiation propagates as a result of being absorbed, which is this term. This is the absorption coefficient. And as a result of radiation, by the warm molecules or scattering. So there'll be no quiz, but to actually calculate things, you have to solve equations like this. They're not terribly difficult to solve these days with very nice computer software, but they were really hard when people got started on this in say 1900. Okay, back to facts. And the most important fact I want you to remember about at this point is that the atmospheric temperature is far from constant. I think we're all familiar with the fact the atmosphere cools as you go up in altitude. That's why if you can get away to the hills or the mountains in the summer, you can have a nice cool vacation rather than being baked in the plains. And the cooling rate is about 10 degrees Fahrenheit, 6 or 7 degrees centigrade per kilometer. And so this cooling continues to somewhere around 10 or 11 kilometers in Princeton or over Dublin, temperate parts of the Earth. It continues to much higher elevations if you go to the equator. So the upper atmosphere in the equator is actually colder than it is over Dublin or Princeton. The coldest part of the atmosphere is over the equator. It seems paradoxical, but that's the fact. And then there's many kilometers where the atmosphere hardly changes in temperature, and then it starts to warm up again. So this warming is due to the absorption of ultraviolet light from the sun by ozone in the stratosphere. And this temperature profile is as important as the absorption by greenhouse gases. Just to give you one feeling for it, if the atmosphere were isothermal, if the temperature were the same from the top to the bottom, you could add all the greenhouse gases you wanted. It would make no difference whatever to the temperature of the Earth. So it's these temperature changes that play a key role in greenhouse warming. For example, if the temperature of the Earth went up with altitude, greenhouse gases would cool the surface, not warm the surface. So temperature profile is very important. So here now is a solution of those complicated equations that I showed you. And I should say a bit about who invented those equations. And there were two scientists around the turn of the 20th century, early 1900s, Max Planck and Karl Schwarzschild. Max Planck is the originator of this blue curve here. So I like to call this blue curve the Planck curve. It's the Planck blackbody spectrum. And the dirty little secret of physics in 1900 was that radiation transfer didn't work. If you actually calculated how much radiation should come out of a warm body, it was infinity. And everyone knew that was wrong, but no one knew quite why. The problem was as you went to shorter wavelengths, you got more and more radiation. The shorter the wavelength, the more radiation came out. And Planck solved that with his inspired guess that energy in radiation has to be quantized. There is a smallest amount of energy at, say, 500 wave numbers that can be emitted or absorbed. And just that simple assumption, which was the beginning of quantum mechanics, was enough to solve the problem. So the first hero is Max Planck. Second hero was Karl Schwarzschild, who was an astrophysicist. And among other things, he was the first person to solve some of Einstein's equations of general relativity. Alas, he died quite early in World War I, not from bullets, but from a rare autoimmune disease while he was posted to the Eastern Front, on the front with Russia. But before he died, among the many good things he did was to figure out this jagged black curve. So I call this a Schwarzschild curve. So the Schwarzschild curve is the curve that describes the emission of the atmosphere when it has greenhouse gases in it. So it differs from Planck. Planck assumed there's a single temperature emitting, and Schwarzschild assumed that it's something like the atmosphere where different layers of the atmosphere have different temperature. So these jags here are due to various greenhouse gases. Here is the absorption of CO2. So CO2 has sucked a lot of energy out from the Planck curve, the blue curve. That's the black curve here. Here's ozone up in the stratosphere. This is water vapor in this region, water vapor in this region. So water is certainly the dominant greenhouse gas, water vapor. And if you include clouds, it's completely dominate. So water is really what controls our climate. CO2 is not completely negligible. So if you were to double CO2, you would go from this black curve to the red curve. So the difference between current CO2 levels, a little more than 400 parts per million now, and doubling those that to 800 is the difference between the black and the red curve. And so the radiation reaching space is the area under these curves. So without CO2, it's 277 watts per square meter. And with CO2, it's 274. So it's only 3 watts per square centimeter difference, about 1%. So important takeaway message is that CO2 is not a very effective greenhouse gas. It only decreases radiation to space by about 1%. If you double it, 100% increase CO2 causes a 1% change of radiation to space. That's what cools the Earth. It doesn't change very much. And the changes are even smaller for the other important greenhouse gases. Here is methane, CH4. You remember this tetrahedral molecule. And here's where methane absorbs. So the black curve is today's concentration. And, you know, I'm sitting right in front of this view graph, and I can just barely see the difference between the black curve and double methane. It'll take a long time to double methane, which is the red curve. So again, and this is less than 1 watt per square meter. So methane is even less effective than CO2. Let me actually backtrack and say one more thing. If you take all the CO2 out of the atmosphere, you get this green curve. So the first 400 parts per million of CO2 has a huge effect. The second 400, doubling it, has almost no effect. So this is called saturation. The effect isn't zero, but it's very, very small. So it's a 1% effect instead of this huge effect of between green and black. Methane's the same. If you take all the methane out, it has a much bigger effect than if you double it. So again, even methane is somewhat saturated. And finally here, well, let me say a little more about methane before I go on to nitrous oxide. You know, the reason methane is around, one of the prime reasons, is life on Earth. And that's because plants, land plants in particular, when they do photosynthesis, a good fraction of their photosynthetic output goes into cellulose, you know, the wood of trees or the fiber in hay and forage. That's almost indigestible by most animals, certainly by humans, you know, by rabbits, all other herbivores, including cattle. So cattle cannot digest cellulose directly. All of the other polymers of sugar that plants make, here, by the way, is the chemical formula of these carbohydrates. The basic unit is a 6-carbon sugar. That's these hexagons here. And they're connected by oxygens in various ways. And the simplest is starch, which you find in potatoes and grains. And a slight variant is pectin here. Makes nice jelly because the branching helps to do that, of these chains of sugars. And we ourselves have glycogen in our muscles. That's what gives us a little pep when we start to run or exercise. But plants actually put most of the sugar not into starch and things that we can digest, but into fiber, into cellulose. And so there's a subtle change in the way the sugars are linked, which makes it almost impossible for most digestive enzymes to break down cellulose. And so cattle, ruminants, are able to do this. But at the price of releasing methane. So let's all remember that the reason there's this pressure on farmers is because cattle, sure enough, they produce methane. It's because the food, the forage that they eat, sits here in the rumen while they chew their cud, and it is chewed on at the same time by various microorganisms, by bacteria, fungi, there are a few other things in there. And these convert the cellulose, the fiber, into useful products that the cow can use, into protein and fatty acids and other useful stuff. So that's why ruminants are so successful. They're all over the world and they have flourished because they all have this chemical factory, their rumen, which is able to work over cellulose and get something useful. Termites do the same thing, but somehow termites get a free pass. Okay, let's come back to the final agricultural greenhouse gas, nitrous oxide. Very similar to methane. As I say, they absorb at nearly the same frequencies. And again, you double nitric oxide, you go from black to red, you can hardly see the difference, less than a watt per square meter. So the message is that there really is very little effect of greenhouse gases, and this has been pumped up into a threat that doesn't exist in reality. Yeah, now, it's one thing to calculate the change of radiation to space, and the room for mischief comes from converting this into a temperature change of the surface. So to first approximation, if you take basic physics, you find that these effects, for example, doubling CO2, would warm the surface by about 1 degree Celsius from doubling. And the reason you read all these scary figures about greenhouse gases, CO2 in particular, but also methane and nitrous oxide, is that the alarm establishment has applied huge feedback, positive feedback factors to the direct warming, which, you know, multiply 1 degree of warming into 3 degrees or 5 degrees or 6 degrees, you know, absurdly large amplification factors. And I should also point out that in reality, in most cases of nature, feedbacks are not positive, they're negative. It even is dignified by a principle, it's called Le Chatelier's principle. And Le Chatelier's principle says that a system, if you perturb it, readjusts in such a way as to diminish the effects of the perturbation. But here we have a system, the climate, which for some reason completely violates Le Chatelier's law, and instead of minimizing the perturbations, it amplifies the perturbations. Now, there are systems that do that. For example, TNT does that. You know, it's an explosive, you know, but there's no evidence that the Earth has this positive feedback. If it did, it's unlikely actually that life would still be around, because there would have been a runaway greenhouse effect long ago, because CO2 levels are always changing and none of them have ever led to catastrophe. Okay, you might ask, I'm just showing you model calculations, but we actually compare our model calculations, William and I, with observations, not with IPCC. And so that's IPCC simply compares different, you know, computer models with each other. We compare our models with data. So here's our modeled radiation from the Sahara Desert. This is measured by a satellite over the Sahara Desert. The dashed curve here is the Planck curve that I mentioned, you know, Max Planck's black body radiation. So you can see CO2, water vapor, you know, ozone. Here's the same comparison of observations of the Mediterranean, where it's not quite as hot as over the Sahara. You notice the vertical scale here is a higher temperature here than here. And again, it's not easy to tell the difference between what we model and what is measured. And there are no adjustments here. And finally, this is over the South Pole. And it's interesting, over the South Pole, this is CO2. There's still a little bit of water vapor, not very much, and still some ozone. But CO2 actually is in emission here rather than absorption. So CO2 over the South Pole, North Pole too, actually cools the Earth. So there's a certain latitude, if you get above that, north or south, that CO2 is actually a cooling agent rather than a warming agent. But most of the Earth, it's like the first two panels here. Okay, so let's talk about CO2 levels of the past. This is an attempt to estimate past levels of CO2 from proxy records. You know, we didn't have people measuring it back then, but there are ways you can look at isotope ratios of carbon-13 and carbon-12. You can look at stomatal indices of fossil leaves, and there are various other attempts of differing reliability to estimate past levels, but they all agree that over most of geological history, since the Cambrian, since sort of higher life evolved, levels have been measured in thousands of parts per million, not a few hundred parts per million. So here we are today, basically in a CO2 famine. So this is today. And so only once in the past have levels gotten close to what they are today. This was the Permian. And actually, whether it's correlated or not, I do point out the largest extinction we ever had of life on Earth was in the Permian. It's quite possible that had nothing to do with CO2 and it was driven by things like flood volcanoes. There are all sorts of competing theories. But our current CO2 levels are low, and life evolved, plants evolved, especially with higher CO2 levels. So plants do much better as you increase CO2 levels. You can see that happening today, especially with forestry, where forestry yields are going up, and yet nobody is planting new varieties of trees or doing a lot of fertilization of forests. So the main reason forests are growing better now is because of more CO2. But agricultural crops are also doing better, and CO2 is part of that, of the reason for that. So here is where CO2 level first started to drop. At the end of the Cretaceous, was the first time they began to drop below 1,000 parts per million. But even at 1,000 parts per million, the Earth was a very verdant place. This was the early Paleocene, and it was warmer than today. There was more CO2, but very likely most of that effect was differences in plate tectonics, that the equator was an open seaway when this period began 60 million years ago. Water could flow freely from what would be the Pacific today to the Atlantic to the Indian Ocean. And life did just fine. It did extremely well. Here's another famous picture. This is Sherwood Idso, Craig Idso's father, with an experiment he did with Eldorika pines, a Turkish pine, at ambient CO2 levels at 150 parts per billion, 300, 450 parts per billion. You can see it was done a few years ago when the ambient was 385 instead of a little over 400, which is what it is today. But the effects of CO2 are dramatic. The more CO2 you have, the faster the plants grow. And this is just, you can't question this. There are just thousands of experiments that demonstrate this happening. Here's sort of a modern satellite era measurement of that. This is the greening of the Earth from CO2 from 1982 to 2010. This was Donahue, an Australian scientist who did this. And let me point out that the greening is most intense at arid regions of the Earth. Here's Western Australia, pretty arid there. Here's the Sahel, the edges of the Sahara Desert. That's where the greening is most intense. Somalia, semi-desert, the Deccan, semi-desert, India, Western US, the Great Basin over here. And that's because one of the major effects of CO2 is not so much fertilization, but more efficient use of water. Here's the Kalahari Desert down there. So most of this greening is not so much fertilization, but plants growing where it used to be too dry for them to grow. Now they can grow there. But there are other benefits as well. This Jim O'Brien kindly gave me from a talk that John Christie gave earlier at this series of talks. And what it displays is how badly the computer models that are used to stoke alarm agree with observations. So this is worth a little bit of discussion. This is measurements of the upper troposphere, just below the tropopause. So it would be, 10 kilometers, 12 kilometers up. This is actually near the equator, I believe it says, and tropical temperature. And the models is this spaghetti curve up here, and the observations down here are from balloons. That's a heavy green curve. And this thin purple curve, I think, is satellite observation. But the balloons and the satellites, which are measuring the temperature directly, give this rate of increase. And models are giving, quite a bit more, 3 or 4 times as much. And the newer models are even more extreme. So the models are getting worse. They're not getting better. They agree worse and worse with observations as the years go by. So as John Christie said, this hypothesis has really failed. Why we're continuing to make policy based on these crazy models is beyond me. So let me summarize, and then I think it'd be useful to have a discussion session. So basic science shows increasing levels of CO2, nitrous oxide, and methane will not cause a climate emergency. This is another extraordinary popular delusion and madness of crowds. It's in line with the sad history of human lust for money and power, folly, and cowardice. More CO2 will benefit life on Earth because of its value to agriculture, forestry, and photosynthetic life in general. More CO2 and methane will have negligible effects on Earth's climate. We already know that from what the climate is doing now in response to the increases of CO2 and other greenhouse gases. So rational people need to push back against climate fanaticism. It's not based on science at all. You shouldn't think in defending your livelihood that you're going against science. Science is on your side. It's on the side of all productive people in the world. And I personally do not think appeasement will work. I don't think it's possible to compromise. This has to come crashing down at some point. I hope I live to see the day. Well, thank you very much. That's all I have to say now.